mentioned two beta functions. So the beta function tells you when you have a theory with a given coupling, how that coupling runs as you integrate out fast modes. In other words, as you zoom out to the infrared, as you go to low energy, how does your coupling behave? And we wrote two beta functions, first for the two-dimensional ON nonlinear sigma model, next for four-dimensional Yang-Mills theory. Both had a very important feature, which was this negative sign, this minus sign, right? Which means that if G is small but positive, right? If the coupling, either what I call G and what I call E0 here, if it's small and positive, and we integrate out, we go to 0, right? The derivative is negative, so we are kicked to 0. And so at high energy, we go to a free theory, and we have what's called asymptotic freedom. However, at low energy, on the contrary, the coupling becomes big, the theory becomes strongly coupled, and we don't have that many tools to study the theories. One tool that was very useful was large N. So how did it work? So first, based just on the beta function, we argued that if particles would acquire a mass, that mass will be non-perturbative, and it will be something like this. That was purely from the analysis of the beta function. And this, when n is very large, behaves like this. You can drop the -2. And indeed, this is what we derived from large n. This was nothing but the expectation value of the Lagrange multiplier. What we saw is that at large n, because the fields are so much, you can integrate them out, and the Lagrange multiplier will be frozen to this constant value plus small fluctuation. And because the Lagrange multiplier is constant, is roughly constant, it means the fields are basically free massive fields. Now, what if you don't go exactly to large n, but you go to n equals 8, very big? Well, then lambda fluctuates a little bit, and so the particles will have some mass, but it will not be just free particles, because lambda is also fluctuating, and so on, and you get a strongly coupled theory of 8 massive particles. When you have the massive particles, the particle has an index A that runs from 1 to n, and symmetry is restored. Right? So we start with ON symmetry, there was no special direction, and indeed you have n particles, you can rotate amongst the n particles, and there is no special direction. In the UV, however, symmetry is broken. Symmetry is broken, and you get n minus 1 massless particles. You can think you are expanding around the North Pole. The classical intuition would be that this would be the good description everywhere, because you have some symmetry. The least energetic configurations would be just the vector being pointed in the North Pole. So why don't we just break the symmetry, go to that vacuum, and then there will be massless modes corresponding to fluctuations around that symmetry breaking state. That would be the classical intuition. That classical intuition is wrong. It's wrong because it's very easy to break order. Order is favored energetically, but entropy wins always. Right? In 2 dimensions, there is always this competition between entropy and the energy, but entropy always wins in 2 dimensions if you have a continuous symmetry. So even though energetically you would like to put all the vectors up, you start putting the vectors up, then they start tilting and moving randomly far away. So you cannot preserve this phase. And indeed, this is precisely what we see. Okay. Now, let me just make a... Yeah.
When you say like large n limit, what would be n? Like what is the order of n that would be considered large?
6. 6 is large, 5 maybe. But in practice, let's try to see what we could say. We could say that n is large. We could imagine that E0 is small, but we could define a limit where E0 goes to 0, n goes to infinity, and this product is fixed. That would be a good scaling, right? So now, indeed, if you look at just the beta function at large n, and you want to ask, when n goes to infinity, what scales nicely? What is a good limit? You see that you would like n is here. Here you get 4 powers of the coupling. Here you only get 2 powers of the coupling. So you could want to do the following. You could want to multiply by n here. And here you would multiply. Let me do it in a different blackboard. You would want to say that the derivative with respect to log of the cutoff of n times E0 squared is equal to minus n, this is, now I'm doing large n, minus n E0 square over 2 pi. Okay? And so this variable, if I say that I start at some energy scale with n very big, E0 very small, and this product fixed, this is a double scaling limit, right? So this would be the natural double scaling limit. E0 would go to 0, n would go to infinity, and E0 square n is held fixed. This is what is natural, because if I start with this limit of large n and E0 small at some energy scale, and then I zoom out, I get that it preserves this limit, right? It evolves nicely with constants of order 1. We could do the same analysis for Young-Mills and ask for Young-Mills what would happen. For Young-Mills, we have that equation over there. Let me write it like this. Let's multiply by g the left-hand side and say that the derivative of g squared with respect to log lambda, let's bring it to a form more similar to what we have, is, well, if I multiply by g, it's something like minus 11 thirds. There is some 1 over 32 pi square. And then there would be a g to the 4 here, n times g to the 4. The 4 is far away for some reason. So now let's try to make the scaling nice. So how would you do it to define a quantity that would be fixed under Rg? Yeah?
Sorry, is it 32 pi squared or 8?
8.
So if I multiply by, 8, good. Thank you. So what should you define? What limit should you take? So what would be the natural limit? So we want to send n to infinity, g to 0. And what would you hold fixed to have a good limit in this equation? How would you do the same game as we did here? Here we saw this is indeed a nice quantity, right? So now here we did not do this analysis, but we can just do it at the level of the beta function. What would you do?
Keep n squared. Multiply.
Very good. So multiply by n, and then you see why I did. And so the natural limit is n to infinity, g to 0, and n times g squared, which is usually called lambda. It's a new coupling. It's called the 't Hooft coupling, would be held fixed. If we start with this limit at some energy scale, and then we flow, we stay in this limit. So this would be a good limit to take large n in non-abelian gauge theory. Which is where we go now. So what we are going to check now is that we study large n non-abelian gauge theories. And in particular, we are going to say and see that they are string theories. Okay. So large n non-abelian gauge theories are theories where your gluon, a mu, which is a function in space-time, has some indices I and j, where this I runs from 1 to n. And therefore, they don't commute. And that's where the non-abelian name comes from. Right? So f, mu, nu would have some I and j, etc. And we are dealing, of course, with non-commuting matrices. Now, for the purpose of today and tomorrow, we are going to study the simplest non-abelian gauge theories, where here x is a point in space-time. So you typically have space-time 4 dimensions, 3 dimensions, 2 dimensions. We are going to consider space-times of 0 dimension. Okay? So we are going to study 0-dimensional gauge theories. In other words, space-time is just a point. There's no space-time. And instead of our gauge field A mu of x, I, and j, we will have simply a matrix M, I, and j. So there is one point, space-time is one single point. And instead of integral over all possible gauge field configurations, we will have a path integral over all possible matrices M. This matrix M, let's still make it this matrix Hermitian. And so if it's an Hermitian matrix, this integration measure is nothing fancy. It is just, you just need to integrate the diagonal elements are real, right? If a matrix is Hermitian. The off-diagonal elements, one is conjugate of the other. So you just need to, for the off-diagonal, to consider I smaller than j, and then real part of mij, imaginary part of mij. So this is what is fancy symbol in this case. The measure means it's something very explicit. You just integrate over the elements of the matrix, and because M is Hermitian, the diagonals are real, and the off-diagonal, the upper part, is the conjugate of the lower part. So this is the integration of all the matrix elements. Then e to the minus the functional of, say, our gauge fields and matter, perhaps, will become an action for this matrix, e to the minus an action for this matrix M, where this action for the matrix M would be, first there is a coupling. Now the coupling, I'm going to put it like this, 1 over 2 g squared, as in Yang-Mills theory. Let me just make a comment that I think, I'm not sure, but I think in the tutorial, you are going to put a normalization n over 2 in the tutorial instead of this. Is it true? Okay, n over 2 in the tutorial. Now it looks very different, 1 over g squared and then over 2, right? It looks different. But as we are going to see, we are going to take the 2th limit soon, where this quantity is fixed. So indeed, 1 over g squared is roughly like n. So it's not so different. They have the same order, right? So this is okay. In the large n limit, these two normalizations are both very natural. They are equivalent. And then we have the kinetic term. That would be, instead of trace of f squared, it would be trace of m squared. And then we could have interactions. And interactions, there could be some general potential that depends on this matrix. This potential could be something like some sum of, for example, there could be some constants Tn times m to the n. Because I put the coupling outside here, these guys are now order 1 numbers. Like for our phi to the 4 theory, if I put the coupling outside, then phi to the 4 comes with coefficient 1 or something like this. And so this could be a general potential.
Yeah. So I understand that, like, because we're in a zero-dimensional space-time, there's no curvature, but how would something like that be gauge invariant, for example?
Okay, so let's answer that. So what would be the analog of gauge invariant? So in the same way that our action before was in f mu nu, how does it transform under a gauge transformation? In an abelian gauge theory, if you do a UN rotation, how does f mu nu, this matrix, transform?
The adjoint representation.
Yeah.
So okay, with a matrix of a group element.
Exactly. So under a gauge transformation, f mu nu at position x transforms under omega, some rotation at position x, f mu nu times the inverse at position x. And that leaves the trace invariant, right? Because you put one f, you put another f, the omega's omega minus 1 cancels, the other outer ones also cancel because of cyclicity of the trace. So this is a symmetry indeed of the action. And similarly now, this analog of this symmetry would be the fact that I can rotate m, I can do a rotation omega m, omega minus 1, and the action is invariant. Right? So this would be a symmetry of the action. Or a redundancy, if you want, of the action. That in practice, even though it looks like all the m matters, in a sense, only the eigenvalues of m should matter. And this would be the analog of the gauge theorem.
But m is analog to the gauge field, right? Gauge field does not transform like that.
No, well, the way I wrote it, m is a matrix. The fields that are matrices become just m. I don't know, a or f. You can put f here if you prefer. I don't know. This is the model. This is the action. Here is m squared. In Yang-Mills, it will be f squared. A or f, if you don't have space-time, it's hard to tell, right? Because you don't have derivatives. So who is A, who is f, whatever. This is the definition. Okay. And so we have our building blocks. So now we can define what are called the zero-dimensional gauge theories that are called matrix models. So our one matrix model, one is because there is one m. If you have m and m prime, it's 2. But there's only one m, so it's called a one matrix model. So our one matrix model, the definition is if you want to compute the expectation value of something, this is defined as the integral with the measure that we defined there of that something times e to the minus direction of m, and by normalization divided by the partition function, which would be just the integral without anything. Okay. So this is the definition of our matrix model. Let me also define the expectation value, maybe with an index 0, to be the same with no potential. In other words, if you want to do perturbation theory, the potential we will treat as a perturbation, bring down, and we'll compute expectation values with this 0. So this is what we do. This is basically what we need if we want to do perturbation theory. Right? The usual thing. We expand around the Gaussian point. Okay, so now let's study this model, and we want to understand the claim why this model is supposed to have anything to do with string theory. Why is this a string theory? So let's start studying these simple expectation values, and let's start with, we have here a bunch of analogs of quantum field theory. The action becomes this, the measure becomes that, the field becomes a matrix. What's the simplest thing you compute in quantum field theory when you want to study some quantum field theory?
2-point function.
2-point function, the propagator, right? So as Manu said, let's study the propagator. The simplest, the simplest quantity you could compute, which would be the expectation value in the Gaussian theory of two fields. So let one of them be Mij and the other be Mkl. Okay, so now I'm not going to do this computation because it's very simple, but let me just tell you how you would do it. You notice that trace of m squared, right? Trace of m squared is what? It's Mij times Mji, right? So it's a Gaussian integral, right? And in particular, it's, yeah. Okay, I'm going to help you a little bit. Trace of m squared is equal to Mij Mji, which is Mii Mii. Now, because I have 4 indices, let me really write the sum 1 to n. These ones are real, the diagonal ones, because m is emission. Plus, and then the other ones, which is a sum over I not equal to j of real part of Mij plus I imaginary part of Mij times the other one with ji, which is just a complex conjugate of this, times the same thing with mine. And so this stuff is real part of Mij squared minus this guy squared, which is plus the imaginary part of Mij squared, right? And so now you are totally ready. You have here, by the way, this guy is the same as the real part of Mii, so this full thing is the real part of Mii squared. And so you really have a diagonal Gaussian expectation where you have real part square, imaginary part square. This m is real plus imaginary, this is real plus imaginary, so you just compute the Gaussian. Correct? Very simple. So what do you get? So first of all, it's the inverse of that stuff. So there is a 1 over g squared there. So the propagator will have some g squared. In your tutorial, you would have n up there, so the propagator would have 1 over n. Again, don't forget that you might need to redo some of the things we did in class with the new normalization of the tutorial. That's the g squared. And then you have real part plus imaginary part, and you have to do this stuff, and you really understand, you can easily see that you get delta function of IL, delta function of JK. That's what you get. And in pictures, you draw it like this. You say that you have a matrix with index I and j, and because the matrix has 2 indices, you write the field as having, you open up the 2 indices, and the index I, which is this, propagates and needs to be identified with index L of the other matrix, and index J of this matrix propagates and needs to be identified with K of this other matrix. And this index I is the first index of the matrix, so let's put an arrow going out. And J is the second index of the matrix, let's put an arrow going in. And then it makes, here it's nice because L now, if I follow the arrow, it has an arrow going in, but that was the prescription for the last index, and it is the last index of the matrix. And J, if I want to preserve the arrows, I need to put an arrow going out, so this is the first index of the matrix. So you see that here you might be a bit, the first time you see it, you might find it weird that first index goes to last and last goes to first, but that's precisely what the picture would like you to do if you follow the arrows. Right? Or said differently, in other words, the matrices like to be contracted like last index with first, last with first, last with first. That's how we multiply matrices. So it's not so surprising that that's the connection, but this is the result of just doing the Gaussian integration with this measure. And of course, you can also, this is one way of drawing it. You can also just say I have a matrix M here that goes to a matrix M here. This would be the usual graph notation. And here what you did is you take this graph and you made it fat. Now instead of a line, it's like a ribbon. And so this is what's called a fat graph. Or sometimes it's called a ribbon graph because it looks like a piece of ribbon that's propagating here. So, and this is the propagator. Okay, so once we know quantum field theory, first step is the propagator. What's second step? To do perturbation theory. What do we do with the propagator? Weak theorem. So now we just now we can compute the expectation value of this potential by bringing down the potential and then just doing weak contraction. Right? So now let's go on. Step number 1 was propagator, and step number 2 is expectation value of interactions by weak contractions. Right? So 2 is now we do interactions by weak theorem. Right? So all we need to do is compute expectation value of some quantities now that we compute in the Gaussian matrix model, and we do it by just using weak theorem that tells us contracting in all possible pairs. So let's consider an example. Suppose from the potential you bring down, so because you bring down from the potential, it's natural to put this 1 over 2g squared downstairs because it was there. And then, for example, you bring down trace of m to the 4. So this would be, in quantum field theory, like expectation value of phi to the 4. What do? You draw all possible contractions between the 4 fields, right? So let's do this computation. So this is 1 over 2g squared. Expectation value of, now let's write the trace, mij, mjk, mkl, mli in the Gaussian theory. Correct? Now you have 4 fields, and all you have to do is take this guy, the first one, and contract it with this, this, or this. Right? Do all possible with contraction. There are 3 terms, right? Because the first guy can marry with the second, the third, or the fourth, right? And then the other 2 are left, and they have to be paired. And so there are 3 terms. Let me maybe put a bracket here so that I don't carry this 1 over 2g squared. And so the first one is m, let's write them all, mij, mjk, followed by mkl, mli, plus the next one would be, the first marries with the third one, mij, mkl, then the other 2 that are free, mjk, mli, and the last one, the first one mij with the last one mli, and then second and third mjk, mkl. All these expectation values with 0, of course.
Is that supposed to be an MKL in the second?
There is R there instead of M. The second term.
Yeah. Okay, thank you. I don't know why I did that. Mij. Okay. And now we are going to do this we are doing it in all detail. It's a bit, but it's the only time we'll do it in detail because now we are going to find soon we are going to find a graphical way of doing this much faster. but let's continue and do it in all detail. Now, this propagator, we worked it out up there. So let's really work it out. So let me continue here, equal. Okay, let me remove these two here. Remove this two. I don't care about this. Now, each propagator comes with a g square. So now 1 over g square, there is 2 propagators. So in total, there will be g square in front instead of 1 over g square because of the 2 propagators. Each propagator with its own g square. And now we just write the Kronecker deltas. First Kronecker delta there is delta I with last, first with last, ik. And now delta jj. You agree? First propagator. Again, first index with last index, always. And then, let me put some parentheses to remind you that it comes from the first term. The second one, mki delta ll, plus, let's go on, delta il delta jk, delta ji delta kl, plus delta ii delta jl, delta jl delta kk. Right? Always first with last, last with first. And now, what does this evaluate to? So let's just see. So j with j, I sum over j, this gives me n. L with L, I sum over L, this gives me n. Delta ik times delta ki gives me delta ii, I sum over I get n. In total, the first term gives me n cubed. You agree? And so we get equal to g square, parentheses, n cubed for the first term. Second term. Someone tell me, what do you get from the second term? Just do it in your head. Whenever you have 2 deltas, you contract the indices, you get 1 delta, you do it. N, right? It's clear? Can everyone see? You just swallow all the indices. At the end, you get a single delta of whichever letter you started with, ii, and that gives n. And the last one. And the last one, n cube again, because there are 2 deltas that I've repeated, and it's the same as the first one, plus n cube. Okay. Now, let's see graphically what we just did. Let's draw these diagrams corresponding to these contractions. Okay. So now we repeat the same graphically. So we have the expectation value of 1 over g squared trace m to the 4. And this would be the expectation value of 1 over g squared, and then trace of m, I write like this. If this is m, with the 2 indices of m, right? Then I multiply by a matrix, which means that if this is I and j, the next matrix has index j and k, and so I just draw it like this. So this would be a product of 2 matrices, this matrix times this matrix. Right? This tells me that this index j is the same here. This was out, this was in, and now this is out. So you see this notation, you follow the arrow, and it just tells you that mij, mjk, j is the last index first, and then it's the first index. And then you continue and you multiply by the next matrix, where the index k is here, and then there is L, and then you multiply by the last one, where you have L and I. So this is how you draw a trace of m to the 4. You just write like this. This is just representing the product of the 4 matrices, keeping track of how the index goes.
Pedro?
Yeah.
I was copying and I didn't see. Can you just repeat this?
Yeah, so I just say, if you draw this matrix, the first one, ij, this is the matrix jk, and what should you do? The j is the same, so you should just connect the index j. So this part here is mij, mjk. Right? In the sense that you keep track of the indices. This line represents the propagator for m. This will be the whatever will be the propagator for the next m. But this index is the same, needs to be the same. So I connect them like this. Right? So this would be the analog in the usual graph notation to just saying that phi to the 4 is just this. Right? But here we make it fat, and now we can follow the indices. Right? So if it was not fat, it would be a pain to see what exactly we are doing. But now that it's fat, it's very easy to just follow the index where the index is. And now we have our fat vertex, and we connect it with fat propagators. Right? So now we just connect with the propagator. So how do we connect here? The first option is this guy connects with this one, and this one connects with this one, right? When we connect here, right? There are this option plus this with this and this with this plus this with this and this with this. Right? The usual weak contractions. Right? Now we are going to do the same, but let's do it here carefully with our fat graphs. So the first one is, as I said, you contract this one with this one, and this one with this one, and then this one with this one, and this one with this one. This is one possibility. Right? You propagate from here to here and from here to here. The other one is the first matrix connects with the third one. So let's draw that one plus. So let's draw that this connects to here and this connects to here. That's the first connecting to the third. And then the second connects to the last one. So I have to draw like this. It passes below, right? And then it goes here. And it goes here. That's the second option. And the last option is the first connects with the last one. So it does directly this. And then the second connects to the third one. Correct? And now you just see that here, the index here, it's the same index, right? It goes around. So here you have a loop, a phase where this index runs, and it can take any value here. And so each time you have a loop of index, you get a factor of n. So here you have a loop, and you get n, because this loop can take any of n values. And how many loops you have? You have a loop here, you have a loop here, and you have a loop for the outer line. Right? And so you get 3 phases or 3 loops, and therefore, so we get 3 loops, or we say it sometimes 3 phases, and therefore n cubed. You can call it phases. You can imagine you put a bit of glass here. Then you did one piece of glass, and one piece of glass for the outside.
Having a loop gives n. How do we see that?
So this just means that you connect, and this can take any value. It can take value 1, 2, 3, 4. So if you sum over all the possible values, you get n.
It's just like this delta.
It's just the delta I. This is delta I, right? You have I here, and this is delta I. But now graphically, it just becomes a loop. What about here? Let's see how many loops we have. Let's follow the lines. So if I follow the line, if I start here, I go here, I go here, I go here, I continue here, I'm here, 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 and I came back. Right? So all in all, a single loop. So this as a single loop or phase, and therefore this diagram gives n to the 1. And this one, again, 3 phases, so n cubed. And so we see right away that graphically these terms have this simple explanation. Okay, now let's continue. So we conclude that we get twice this diagram, right? The first and third are the same type of diagram topologically. Right? And this diagram here is what we call, is a diagram that I can draw on a sphere. I can put a sphere, and I just draw it here on the face, on my sphere, on the plane. This is just a sphere. And because I can draw it on the plane or on the sphere, this diagram here, this diagram is called a planar diagram. It's also, we can also say it's a graph of genus 0. The graph I can put on this sphere which has no gene. Now the next graph plus, then I get the other graph, this one where I connect like this, and then I need to go around. And this diagram, you see, I cannot draw on the plane without lifting the chalk. Right? I cannot draw on the blackboard without lifting the chalk. It cannot be put on the plane. This diagram cannot be drawn on a sphere without or on the plane. Now, you can, however, draw it on a donut. So if you have a donut, which is a genus 1 surface, so now this is not a sphere, this is a genus 1 surface. Now you can draw this graph here. You just start drawing the quartic interaction here. Okay. And you want to connect these points without crossing these lines, without going over. And you want, so this, you connect with this, you connect with this. Right? But now, you can indeed connect them without going below, by just going around and connecting like this. And this diagram is therefore called, whereas this is a planar diagram, this is a non-planar diagram. In this particular case, is a genus 1 diagram, meaning that it's a diagram that can be drawn on a surface of genus 1. Another way of drawing this same picture is thinking that a donut is just a square with identifications, like a cylinder. You identify this with this, right? And then to make it into a donut, you identify this and this. Right? And now, this fancy 3D picture is just this trivial picture where I just draw it like this. This makes it obvious that I don't need to lift the pen, right? And if I identify now things, I get precisely that picture. So what we are seeing here is that we are getting that planar diagrams, at least in this simple example, when n is large, they give bigger results. That is n cubed versus n. More precisely, let's summarize here what we found. Now with all factors of g squared, 1 over g squared trace of m to the 4 expectation value was equal. Now let's write like this. Let's say, okay, let me write first. It was g squared n cubed with a 2 plus g squared n. That was the result. But let me rewrite this. Knowing that the nice Tuft coupling is what we wrote up there, let me write it as saying that this is n squared times 2 g squared n plus g squared n. And this quantity here, g squared n, is what we define as the Tuft coupling, lambda. This quantity here is therefore also lambda. And therefore, if this quantity, lambda, the Tuft coupling, is held finite, then we get n squared for the planar diagram and n to the 0 to the non-planar diagram. And so these diagrams, this here, they are dominant at large n. Now, let's work out one more. Yeah, I have time. Let's work out one more example. And after working out this example, we will prove a general theorem. Let's work out another example. Let's suppose now I have the cubic coupling. We did the quartic coupling. Let's do the cubic coupling. Okay, so let's do that. Expectation value, 1 over g squared trace of m cubed. What will be this expectation value?
Should be 0.
0. I have 3. Okay, so this example is done. So maybe let's do one more. If we have 1 cubic, it's 0. What do I need if I want cubic vertex? 4 I did already. So I want cubic.
6.
So then I need 2 of them. I need to bring down from the exponent 2 of them. So that's okay. Now we want to do this example. Okay, so let's work it out. So now it's very easy. We do it graphically. So it's 1 over g to the 4 times the expectation value of the first one, which is just now some cubic, And then the second one, another cubic n. And then all we have to do is we contract. Is contract these propagators like this. Right? So there are a bunch of options. There is. So first of all, how many propagators there will be in total?
3.
3 propagators, right? I need to connect, right? I need 3 propagators, for example. And connect like this, and like this. 3 propagators. And therefore, this 1 over g to the 4, each propagator as g squared, will become, like before, a g squared upstairs. Right? Each propagator has g squared. And then, let's draw the graphs that we have. So one possibility is what I drew here. So let's draw it. So one possibility is this goes here, this goes here, this goes here, this goes here. This is one possibility of contracting. Let's work out one more, or the other ones. What else could I do?
They come to each side to itself and one.
Very good. As Ami said, you contract 2 of them within the same operator, then they contract to the next one. Right? That's another possibility. Last one. There's one more. Notice that if they self-contract, it's the only option, right?
Yeah.
Because as soon as they self-contract, there's only one option. So it means they don't self-contract. So if they don't self-contract, it means that, okay, there is one propagator between them. So I can draw the beginning. Now what can I do?
Cross it. This one.
Right. So instead of connecting like this in the friendly way, I connect in the non-planar way. Right. So I connect this one with this one. And now the other one is not happy because it cannot connect. Okay, it's life. And you need to draw. Yes. And then like it. Correct? What symmetry factors do we have? What factors do we have? How many terms are there for each of them?
The middle one is 3.
Sorry?
The middle one is 3. Right?
Let's see. The middle one, okay, you can, okay. The middle one is 3. What was the argument? How was your counting?
Because we have one that there is. Okay.
If I chose that out of, if you look at one diagram, out of 3, you have to choose 2 branches. So 3 choose 2 is 3, and then everything gets fixed automatically. Because you choose one, in one diagram, choose any 2 and connect them. Everything else is already fixed.
So you say in one diagram, choose 2 to connect. So there are 3 options, right?
3 options in there.
And in the other diagram?
Because in the other diagram, okay, then you could have
I
3.
think one of them should be 2, one of them should be 1. Right? Because in general we have 6 options.
You choose 2 into 3, maybe 9 it should be. 3 square.
Oh, 9. Someone else, Manu says. Who is right? Manu or Hami? What do you think? So again, you have to just do weak contractions. So there are many ways of thinking. Let's go with what they said. So we decide first, we take the first operator, and we choose who is not going to be contracted, or we choose who is going to be contracted. Same thing. There are 3 options. We take the second operator, and we choose who is not going to be contracted. There are 3 options. 3 times 3 is 9. Yeah, so correct is 9. What about here? Here, everyone here needs to connect to everyone here, right? How do we think? So the first guy
That's 3 choices.
has to connect somewhere there, and it has 3 choices. Right? And that's it. Once that's done, the other ones you just follow clockwise. Right? 3. The last one.
3 again.
3 again. You just say who connects. That's 3 options. And then the other ones are fixed by topology. 3. Let's do a check. 3 plus 9 plus 3. If you add them up, 3 plus 9 plus 3 is 15.
That's the contractions for
Sorry? And 15 is 5 double factorial, right? What is this 5 double factorial? It will be the number of weak contractions if you add just 6 fields and you don't care about them and you just have 6 fields, right? And so you say the first one can choose any of 5 options, then the next one can choose 3 options, and the next one can choose 1 option. So whenever you have n fields, you would get always n minus 1 double factorial total number of diagrams, and that's okay. That's what we are getting. Okay, and now let's see what this gives us from loops. How many loops we have? Here we have one loop here, one loop here, one loop outside. This diagram gives n cube. What about this?
N cube again.
N cube as well. What about that? Follow the loop.
This is just one loop.
It's just one loop. N. And same story. This diagram can be drawn on the plane. This diagram can be drawn on the plane. This diagram can be drawn on genus 1 surface. So again, these ones are planar. And this guy is genus 1. And what we get in total, just to work it out, is, if I write, there are these diagrams, 9 plus 3 is 12. Let me write this 12 times g square n times n cube times n square plus, and then 3 times g square n as before. So 12 lambda n square plus 3 lambda. So we see that the planar graphs not only are dominant, but they come with the same n square here. Right? They are dominant over the non-planar, but more than that, it looks like we are getting, from this very simple example, we are seeing some pattern. And the pattern is that we get n square times some function of the 't Hooft coupling plus n to the 0 times some other function of the 't Hooft coupling plus dot dot dot, where this would be planar and these guys would be genus 1. So normally it would be a good point to stop and start the next lecture by proving this statement. I wonder if I should go 5 minutes over time and prove it now for the purpose of the tutorial, or you think it's okay to stop here?
What are you going to prove?
To show that these diagrams, to do this Euler characteristic stuff and to show in the tutorial. Okay, so very good. So we see this pattern. And so we would like now to establish this in full generality, which you are going to do in the tutorial. And then I'll start tomorrow by recalling how that goes. And indeed, the conclusion is precisely that. But just to conclude, let me just say one thing, that what we are seeing is that the diagrams like to organize themselves by topologies. Genus 0 are the most important ones, then genus 1, then genus 2, then genus 3, etc. But that's what string theory is. String theory is defined as a sum over topologies. You have strings interacting, then strings can split and join again, and that's subleading, and then strings can join and split many times, and that's more subleading, etc. And so the kind of diagrams that we are getting are diagrams that like to be split into genus 0 surfaces, genus 1 surfaces, genus 2 surfaces, etc., exactly like string theory. And because you sum over all possible diagrams on these surfaces, it's like you are discretizing these surfaces. So summing over all possible diagrams that you can draw on the sphere is like doing a triangulation of all possible spheres. And then summing over all diagrams on the donut is like summing over all possible genus 1 surfaces, and so on and so forth. And so that's how we will see that indeed the summation over these graphs you can interpret as a genus expansion of a string theory. And that's why large and gauge theories are string theories. But that's what we are going to finish concluding tomorrow. Okay. Matrix model. There is a single matrix we integrate over, and so we call it a one matrix model. Then we add exponential of minus 1 over g square, and then we have trace. We can have our kinetic term, 1/2 of m square, plus, and then we could have some general potentials. We could have some T3 m cube plus some T4 m to the 4 plus dot dot dot. And then we treated this in perturbation theory by bringing this guy down from the action, and then we compute expectation value of stuff like product of traces of m to some powers ni, maybe they appear some trace a given number mi of times in the Gaussian theory. This is better. Okay, so then we would multiply, we would have to compute this expectation value. I would make a product from n equals 3 up to infinity of some objects like this, right? So when n, we did a few cases where we only had n equals 4, 1, so this m would be 1 for m4 and 0 for everyone else. And we did one case where we did 2 trace of m cubed, so this guy would be 2 for n equals 3 and 0 otherwise. But then, these guys, then we would compute by just doing some weak theorem. And when we did it, we saw that planar graphs have more faces, also called loops, and therefore they dominate. Okay, so let's try to see this in general. So let's try to work out the contribution from a given contraction like this. So let's consider now a general diagram, a general graph. Now, for a general graph, what would we have? Let's work out the general power of counting and so on. Well, first of all, if we have, each time we bring down a vertex, we pay a factor, 1 over g squared to the number of vertices. That's v, right? Then each time we have a propagator, we have an edge, we get a propagator which is a factor of plus g squared. So we get g squared to the power of number of edges of the graph. And what about faces? Each time we have a face, we get a factor of n, right? Each time we have a face, we get n to the number of faces or loops of the graph. Now, here comes an important fact, which is that there is a relation between these three numbers that goes like this, that the number of vertices plus the number of faces minus the number of edges of a graph is a topological quantity that's called the Euler characteristic that measures the genus of the graph. And so this quantity is equal to twice minus twice the genus of the graph, where this genus of the graph is the minimum genus of a surface sigma where we can draw the graph. Right? Of course, if the graph is planar, I can also draw it on a donut, right? But the sphere would be the minimum genus. But if the graph needs a donut to draw, I cannot put it on the sphere. So the donut is the minimum. Of course, if I can draw it on a donut, I can draw it on a donut with genus 2. So the genus of the graph is always the minimum, the genus we can put. This quantity here is what is called the Euler characteristic. And people normally call it chi. Let's just do a check. Let's draw a cube. Did everyone reach this part of the tutorial yesterday where you were asked to think of a cube? So did everyone do this part? Who reached the cube in the tutorial? There's no cube in the tutorial?
There's lots of diagram there.
Okay, good. So this cube, let's imagine this graph. This graph, clearly I can draw it on the sphere, right? I can just put the sphere and put the points, the 8 points on the sphere and just draw the lines, right? So of course we can put it, we can embed this on a sphere, right? I'm not going to try to draw it. It's just you put a cube inscribed on a sphere. So you can draw it. And let's count the number of vertices plus faces minus edges. Number of vertices, you have 8. Right? So 8 plus number of faces, you get 6. Minus number of edges, you get 12. 4 plus 4 in the bottom plus 4 on the sides. And this is indeed equal to 2. And because we have genus 0 there. Yeah. How would I draw a graph that would correspond to genus 1? What would be the simplest way of drawing a graph like the cube but for genus 1? Well, the simplest is maybe one of the ones that we drew yesterday. But more in this spirit of Platonic solids. What would be a simple solid that would look like genus 1 instead of the cube? How would you transform a cube into a genus 1 surface? Let's put a hole in the cube. So how would you put a hole in the cube? Let's draw the cube. And how would you put the hole now?
like a cylinder.
Cylinder, I don't like cylinders. Cylinders have round edges with straight edges. A square at the top and the bottom. Or we could, what's her name? Sorry, Kelly. As Kelly is proposing, we could do a square here, right? That would go here. And this looks like a nice genus 1 surface, right? It's a cube with a hole in the middle. So is this statement familiar to everyone? Who knew this statement before? This simple statement in topology. Almost everyone knew it, right? Okay, who did not know it before? Okay, everyone knew it. So can you do the counting here and tell me what you get? Who said 0? Did you do the counting or you knew? So tell me, Charlie, right? What's the counting? Tell me the number of vertices.
So it should be the same as the cube, but you reduce 2 because the inner cube doesn't have the top and bottom faces.
Number of vertices. So you're making an argument for the full result. Right, but I would like the counting. I would like the number of vertices, etc. So how many vertices does this object have?
16.
16, good. Plus, how many faces?
12.
Is it 12? 4, 5, 6, 7, 8, 9, 10. 10. 10.
It's 2 cubes minus the 2 faces. So.
Edges, how many edges?
26.
Twice as many as the cube, right? 24. Right? My God. Got a problem.
For some reason, I feel like we can't count the top and the bottom as faces.
Do you have to add 2 edges to connect the 2
Yeah,
faces?
to connect.
Yeah. Good, maybe that could be the answer. Why do you think that would be the case?
They're not like the other ones. They've got a hole in the middle.
Exactly. Exactly. Sorry, can you remind your name again? Sorry. Yeah, as Kelly pointed out, the theorem says that these faces, when you do these faces, they must be contractible. The loops, they cannot have holes in them. Okay. And so here it will not apply. So let's make it apply. So what could we do to make it to make this shape into something where this would apply? We could, for example, I don't know, lift this a little bit so that we would add some extra vertices here, right? Right now it's lifted a little bit, right? So we make like a small truncated pyramid on top. Now each face here is contractible. Kelly would be happier. And here we would lift a little bit. And now each face in the bottom is contractible. Right? And now if you repeat the counting, you scratch this, and you do the proper counting, and you will get it. Okay? I am. I can leave it as exercise. So, how do we go about proving this relation before we go on and checking what's the implication? I think everyone knows about this relation. Few people know about simple proofs of this relation. So let me just show you one simple proof of this relation that I think is worth knowing. Maybe there are other simple proofs, but for me, this is my favorite one. So let me tell you. So suppose we have a graph that we can draw on the sphere. So here is a sphere, topologically. And then there is some graph that we can draw here. It could be something like our cube, or it can be any graph that you can draw on the sphere. Right? So it can be something, anything that you can draw on the sphere. An example, planar graph. Right? So this is an example. So here we want to show this relation for a planar graph. So we want to show that if you have a planar graph, we always get 2 on the right-hand side. Now, here is a derivation of that statement. Take this graph and make this graph with metal. And now take your favorite vertex and insert some electric current here, I. And take another vertex, your favorite one, doesn't matter, and remove the current I from here. Right? So you pick your graph, you make it of pieces of metal, right? And then you inject current at one cusp, at one vertex, and you remove the current at some other vertex, right? And then electric current will flow through the graph from one point to the other. And we should determine the current, we can determine the current at each edge, right? So let's count variables and equations that we need to determine the current at each edge. So we will have E currents, right? At each edge there is a current. We inject the current, we remove the current, so there are E currents. And so E currents is our number of variables. This is what we want to know. We want to know how many, what's the current at each point in the graph. And now let's see the number of equations, right? So now we want to say that this is equal to the number of equations. Let's write the number of equations. So what equations do we have to determine this current? Right, so what to determine the current? So first,
Left for each vertex for conservation.
at each vertex, we have conservation of current. How many equations that gives us? It's almost V, but not exactly V. V minus 1, because if you impose conservation at all possible vertices, at the last one, it's automatic. Right? So we have V minus 1 equations. These come from conservation of current. Right? Plus, what other equations do we have?
Potential for phase.
Very good. At each phase, if you measure the total potential as you go around, it must be 0. And here you see why it's crucial, Kelly's condition, that you cannot have holes. Right? You need to make sure that indeed it's topologically trivial. And so now we have the condition that at each phase, so this is, if I have a phase, I start here, and my total delta V must be equal to 0 if I go around. And again, there is minus 1, right? The simplest, let's draw here a simplest possible graph. If I inject current here and I remove here, right? Again, momentum conservation, imposing here, it's enough. And 0 potential, imposing here, automatically outside is enough. Right? If I have 0 potential from here to here, I have outside as well. So also, phases minus 1. The very last phase is automatic. Right? So these two guys need to be the same. And we are done. We conclude that vertices plus number of faces minus number of edges equal to 2. Right? And this now also generalizes to genus, because if you now have a genus surface, you have to further impose that you get no difference of potential around the 2 new cycles of the torus. Right? So if we have a genus 1, now we have 2 extra conditions, which are the absence of potential. This, if I measure the total difference of potential as I go around here, or if I measure the total difference of potential I go around here, the total delta V must be equal to 0. Etc., etc. Each time I go in genus, I get 2 more conditions for the 2 new cycles. And therefore, this 2 becomes 2 minus 2G.
What is the 2 extra condition? Is it already going along?
It's the fact that there is no difference of potential as I go around this cycle or around this cycle. These are 2 independent cycles of the torus. And each time I add an extra genus, I have 2 new independent cycles. And so the number of equations increases by 2 times the number of genus, and therefore we get a precise equation.
So, but and also in this case, when you said that the phase should be contractible, but in for delta V to be 0, there is no condition of the phase to be contractible. Right? You go along the loop, it will always be 0.
I think that one comes from current.
Okay, so maybe I said, okay. Okay, so this is the derivation. Let's see, where does it enter that the phase needs to be contractible?
It's like if there was a hole in between and there was changing magnetic field, it could induce an EMF. But
Yeah, in this particular case, if there was a hole in the middle, right, this would be like two disconnected graphs from the point of view of this graph here, right? So if I don't put these edges, it's like I have the graph that is the outer cube and the graph that is the inner cube, right? And so indeed, from this argument, if I inject current in the outer cube, there will be nothing in the inner cube. So I will need to inject it as well, and then it will be like computing two planar graphs separately.
Maybe we can say every edge should be connected.
Right.
We cannot have two disconnected graphs.
Exactly. Good. Okay. Anyway, this was as you guys said, you knew this stuff already, so this is just for fun. Just we have a new derivation. Did people knew this derivation? Who knew?
You did that, so I.
Nice. Yes. In Brazil, yeah, very good. Okay. Good. Okay, so let's go on with our general diagram estimate. So we are there. So we continue from here. Yeah, we are there. And so with our general graph, we conclude that our graph scales. Let me see, what do I want to do? So I just wrote again, n to the number of faces, g squared to the number of edges minus vertices. So I just copied what is there. And then, using that relation over there, I wrote this apparently as n to the 2 minus 2g. So I replaced f by 2 minus 2g plus that quantity. And then what appears here is g squared times n to the power of edges minus vertices. And so what's crucial is that you see that a graph that has some edges and some vertices, right? This is just the 't Hooft coupling lambda that is held fixed. And all graphs of the same topology come with the same factor of n in front. And that's exactly what we had observed, that we're getting that all planar graphs are proportional to n squared. And so we conclude that if I sum over all graphs, right, I can write this as a summation over the genus G, right? Then each genus G will give me some factor of n to the 2 minus 2g. And then I sum over all graphs of genus G. Right? And then that summation will come with some symmetry factor times lambda to the power e minus v. This is just some counting of how many equivalent graphs there are, like these 3, 9, and so on that we were getting. And this full thing here, now I could say, defines for me a function f that depends on the genus G, and that is just a function of the 't Hooft coupling. And so what we get is precisely as in a string theory. We get n squared times a function that describes all possible planar graphs, plus n to the 0 times a function that will describe all graphs of genus 1, plus n to the minus 2 times all surfaces, all graphs that I need to draw on surfaces of genus 2, plus dot, dot, dot. Okay. Now here, actually, I'm kind of implicitly assuming that I sum over all connected graphs, right? At least in this picture. I never drew a sphere times a sphere. Well, let's actually be precise. Let's say that here we sum over all connected graphs. Right? And then what would this quantity be? What should I put here so that I really have an equation? What function would this be? What should I put here? Well, let me remind you, the quantity we defined was this integral here. This full quantity here, I did not give it a name, but let me give it now, is what we would call the partition function. Should I put z on the left-hand side of that equation? Not really, right? Because z, when I expand, when I bring down, say, trace of m to the 4, twice, right? I have the disconnected graphs, why not? Right? So it's not z that I should put on the left. What should I put? Log of z, right? When you have z, a summation over all diagrams, you take logarithm to compute what's called the free energy, f where f is log of z. So z is like a gas of strings. It has disconnected components, right? So it has a sum of all planar graph square, planar graph cube, etc. And so it's really a gas of strings. And f, the free energy, we see this free energy, this is like a single string partition function, whereas this would be a gas of strings partition function. Take the log to kill the disconnected graphs as usual. And so this here is equal, becomes identified with a string theory expansion. With, if we identify this n with n to the power -1, related, being what you would normally call the string coupling. Right? In other words, this graph here, what happens to this? I need a probability of splitting the string, creating two strings, and then annihilating it again. So this graph should be G string square compared to this. Right? I need a G string to create those two strings, a G string to annihilate. This graph, I need to create, join, so G string to the 4 compared to this. And indeed, n to the 4 is the difference. Right? And so if I identify 1 over n with G string, it looks like this is automatically what I would expect for a string expansion. Now, let's check this string picture. Let's develop this string picture a little bit more in the remaining 20 minutes. So here, we conclude, in particular, that, so let's make some tentative dictionary.
I have a question.
Yeah.
Why can we make this conclusion when our target space is just a point? Don't we need like specific numbers of dimensions or other things for string theory to make sense? Why is this okay to think about it this way?
Okay. Yeah. So first of all, you don't know what the target space is at this point, right?
We assumed it's a because we're not doing the or maybe today we
be careful. We have 0 dimensions. They are mapped to a matrix M. M is the target space. So what is M? M is an n by n object, not a point, right? So then the question is, okay, this M, the summations of all this matrix M, they define something that has the structure of a string theory. But to identify properly the variables, to say, is this M describing, what kind of dimension is this M describing, you need to work harder. You don't know a priori what's the target space of this map. So just to confuse you a little bit, let me give you an example. Suppose we have, instead of one matrix M, suppose I have 4 matrices, Mx, My, Mz, and M time. Right? Now we have a 4-dimensional target space. You would say that you have 4 components, X, Y, Z, and T. Right? And now you could do computations where you are still computing, say, you put some expectation value of some trace of M in the direction X 4 times, etc. And you compute some correlation function like this. And this topologically would look like you are considering some correlation function of some strings. Now, what exactly is the target space? Is it 4-dimensional as it indicates here, or is it 1-dimensional? The precise target space, we don't know. I think at this point, we need a better dictionary. You need to understand what are the dimensions. We need still to work out a little bit harder in our dictionary. Yeah. Wow. So what would be our tentative dictionary? So first, 1 over n, we said if this dictionary works with string theory, this should be related to the string coupling. The 't coupling, lambda, which is G square n, which, by the way, now we proved that this is the good scaling. Yesterday we had guessed based on the beta function that it was probably a good scaling. Today we proved it, right? Because we saw that the graphs do organize as functions of lambda for a given genus. What would this be the analog of? Remember that in string theory you have 2 parameters. The string coupling, that tells you what's the probability of string splitting, and the string tension, that govern the fluctuations of a string. Right? So this would be related to the string coupling because it's about splitting and joining higher genus. Whereas this tufted coupling lambda, what would it be? If lambda is very small, the diagrams that dominate are very boring diagrams with very few loops. Right? The more loops you have, the more faces and edges you have, the more powers of lambda you have. As lambda starts increasing, you start to have more and more graphs that matter. And eventually you could imagine that you have some dense shapes. The surfaces become very dense and all graphs matter. Right? And so the picture is that as lambda is increasing, you are going towards a more and more classical string description where the string tension should be big. And you have some smooth surface. But as lambda goes to 0, the string tension should become very small and the fluctuations are very wild and you don't have some classical limit. And so it's still tentative. We are kind of arguing, but we would say lambda, or maybe some function of lambda, or lambda to some power or something like that, should be identified with the string tension. Right? And this would be the string coupling. Basically, the intuition here is that large T would mean some classical smooth surface that we kind of visualize as having a surface that is triangulated very, very much, right? Which is like some huge graph. And therefore, we think of this as coupling, some big coupling, such that these big graphs dominate. Whereas small tension would mean that all surfaces matter and it's something very crazy, and then you could have some crazy small graphs dominate. Anyway, this is just some guesses. Everything here is hand waving at this point. We'll try to make this very rigorous next week. But then, what else do we do in string theory? What are the rules of the game in string theory? By the way, who had string theory? Who is not taking string theory and does not have string? Is string theory going on? Yeah, okay. So string theory is a theory where at this level of cartoons you are following, right? So there is a splitting probability, there is a tension probability, and in string theory what you do is you compute expectation values, say on a given genus, say genus 1, of what are called vertex operators. So you insert some vertex operators V, say some vertex operator V1, some V2, some V3, and then you compute expectation value of these vertex operators on some surface of genus G, and this is what describes the amplitude for these two strings going into one string. So there is an operator V1, V2, V3 that insert a string. And so we have this vertex operator V that inserts the string. V, the vertex operator, creating a string. And the claim is that the picture here is that this should correspond to some local operator, like schematically trace of m to some power L. So this one is easy to see, so let's see this last one. Why do we say that these kind of objects create a string? So indeed, suppose we consider the expectation value of two of these guys, 1 over g squared, it's our favorite normalization, 1 over m to the L, 1 over g squared trace of m to the L. And here I'm doing it, you see I'm not putting a 0 here, so here I'm doing it in the full matrix model. Not in the Gaussian matrix model, in the full one. So what are we instructed to do to compute this in the full matrix model? We insert this operator, we insert this one, and then we bring down from the vertex the other interactions many, many times. Right? And we start drawing all possible graphs. Now, let's first spend a few seconds drawing this graph here. We drew it last time, and we drew it like this. But let me draw it in a few equivalent ways, and then we'll pick our favorite to say that this looks like a string propagating from one point to another. So this is one way of drawing this, that you follow the indices. If all you care is about following the indices, you can draw it like this as well. Right? You just open it up a little bit. 1, 2, 3, 4, just one more. Right? This is the same thing. I just blew it up in the middle so that I see the index a little bit better. And another way that I could use to draw this picture is I can just say the last and first index are the same, and then I could draw it like this. All these pictures would be the same. I need to keep in mind that this is one operator, this is one operator, and this whole thing is one operator. I just keep track of the indexes. Right? And then we have the other operator, and we need to contract them. So let's try to draw it, and I'll try to draw it. We have a sphere. We have two punctures, so it's like a cylinder, like when we discussed CFT, that we discussed, right? That a cylinder with a sphere with two punctures like a cylinder. So let's make that manifest. So let's use a representation like this for our first operator, and a similar representation for our second operator like this. And let's draw it, instead of putting the 1 point in the north pole of the sphere and 1 at the south pole, let's put them in, let's open up the sphere and make it into a cylinder. Did you get what I'm doing? So I have a sphere, and I put one of these guys at the north pole. At the south pole, I choose to put the other guy. One guy at the north pole, one guy at the south pole, and then I just draw that sphere as a cylinder. So let's draw it here. If I draw that sphere as a cylinder, so I have the top of the cylinder where I have this index that I follow. I'm not sure if I'm going to regret drawing it in 3D, hopefully not. So here is the top of the cylinder. Then I have my cylinder, and then I have the bottom part of my cylinder. And then we have to draw the weak contractions that connect these operators, right? But also bringing down vertices and adding more vertices along the game. So let's start drawing this picture. So let's, for example, this line would want to contract with this line. Something like this. But maybe here, for example, you can connect with a cubic vertex. And here, maybe we can connect with some quartic vertex. We can meet some quartic vertex. This would be one diagram that would show up in some weak contractions, where you bring down from the action a quartic vertex and a cubic vertex, and you connect like this. And then this graph could connect here, and this could be, I don't know, another quartic vertex that would come from the action. And this guy here could do something, I don't know, like this, for example. It can meet some cubic vertices and do something like this. All these graphs, they must be planar if we are considering the leading order in N. So I need to draw them always on the surface of the cylinder. And then this line could just go here. Maybe it goes directly. Maybe it also meets some cubic vertex. And this one goes here. And it interacts here. Maybe at some point it goes to the other side. And now that it goes to the other side here, it could go on like this. And here it could meet this other guy. Continue going up, right? And this line met this other one. And because this one is hard to draw, I'll just make it go up, connect there. And this line could then also just go down all the way and connect here. Maybe here at some point they choose to do this. Then connect here. And here, guys could just connect. And this is one graph with a few vertices. But as you imagine, as you put more and more and more vertices, this looks very much like starting with some string and summing over all possible shapes of the string that goes from here to here. So the idea would be that you take this thing and you sum over all possible diagrams that fill in the cylinder. And this would be equivalent to starting with a vertex operator here, putting another vertex operator for the bra, and integrating over the shapes of the string. At least in pictures, it looks the same, right? I mean, summing over all possible diagrams would be not changing the topology is fixed, but integrating over the shape of the string. Right? Here we would have e to the minus the string tension times the action of the string. And so these operators, these traces, have the right topology to look like a string, like a closed string that we would insert. So here, this would be creating a closed string, not an open one, closed one. And then this object here would be inserting, creating the string. Right? So this is like a string coming in. And this would be like the string going up. Now, let's continue to see if this picture makes sense. What happens if I have not one string evolving, but two strings evolving? What would they do? If I have two strings evolving, to leading order, what would they do? if the coupling of the strings is very small, what do they like to do to leading order?
We go separately, then go separately.
They go separately. They just propagate separately, and there's nothing special. So let's check that. So now here we saw that if I sum over all planar diagrams, in other words, all diagrams that fill in the cylinder, this would be equivalent to integrating over all genus 0 surface that connect the string to the string. Okay, so that's already one element that backs this interpretation. Now let's think a little bit about the two strings propagating. Now, if I have two strings, I would have one operator O1, O2, O3, and O4. Right? And we want to try to say that these two guys, okay, we just have this. Right? We have 4 strings, so we have 4 operators. Right? We have 2 in the beginning, 2 at the end. Now, this diagram here, connected, scales as what? If I have a connected diagram, we saw the general scaling of a general diagram, right? So the planar one, the connected one, scales as, it's there, right? N squared. Right? Any connected diagram that I draw on the sphere scales like N squared. What about, but then the correlation function, O1, O2, O3, O4, if I write that this could be some disconnected parts, O1, O2, O3, O4, for example, plus connected, right? Where these guys would be now connected. Now, I could have a priori, you could say it could be 1, 2, it could be 1, 3, it could be 1, 4. I could have all possible pairs. Let's suppose we forbid that. For example, let's suppose that we make this O1 and O2 be some trace of some M to the L. It's going to make it a mess. Okay. Plus other pairs. Okay, fine. We can have other pairs. But then we have the disconnected part and the connected part. Now, how does a connected diagram scale? Any connected diagram, N squared. And so we conclude that this gives me N to the 4 times the disconnected contribution, where I have just the 2 strings propagating. And if I put a parenthesis here, plus the connected diagram, which would now come with a 1 over N squared times the diagram where they would interact in a connected way like this. You agree? And so precisely we identify that this 1 over N squared is indeed what we said before, G string squared. There is a probability of annihilating, a probability of splitting again, probability of joining and annihilating, so it works perfectly. And we conclude that at large N, strings are free. By free, we mean they have no coupling. It doesn't mean they are trivial. It's still quantum mechanically very complicated. You still need to sum over the shape of the string. But 2 strings at large N, they behave freely. They don't interact with each other. Right? They quantum mechanically evolve in a complicated way. You still need to do all the planar graphs, which is still very complicated. But we back up this intuition that these graphs dominate over this. Now, of course, and this is string 1, this is string 2, this is string 3, this is string 4, and the other pairs as well that you could consider. But typically, if it was a realistic case, for example, you could force 1 and 3 to be in the past and 2 and 4 to be in the future. A very trivial way of doing this would be, for example, considering some complex matrix M instead of a real matrix, so that this matrix would have some charge. Then you could put some incoming charge that needs to be preserved, and you cannot just start flipping them around. Or you can give colors to this matrix and giving flavor. So you can decorate this a little bit such that you would have only one diagram. Otherwise, if they are neutral, you have all possible channels, which is also what we have in quantum field theory, right? When you do a 4-point function, you also have the 4 disconnected channels, which are just the directions where you look at. When you swap time, it's just crossing symmetry. So let's finish this analogy to see in one more simple example. How this would go. One more example, let's consider the interaction of 3 strings. right? The connected part. Now this would be like considering some interaction of three strings. But we should normalize it properly, right? If we want to really say this is a normalization, I should make sure each one has one 2-point function. So I need to divide by the connected 2-point function to the power 3/2. Do you agree? This is the same as saying that each 2-point function is normalized to 1. And this would scale, well, each of these boys is n squared, so n squared, 3/2, and so in total, 1/n, which is precisely what should be the definition of the string coupling. Okay, this is just one more example, and of course, all these examples would work. Let me conclude with a maybe a small provocation, given that you just learned the planar limit. Maybe it's a little bit too early to already try to confuse you a little bit, but okay, I'll do it nonetheless. So, if L is of order 1, we saw that this trace of M to the L, we want to identify this in our dictionary to a string. I did not say that L is of order 1, but I'm saying now. Now, let's think what would happen if L would be order n. Then we need to be a little bit careful, right? We always were drawing the diagrams assuming the operators were of finite size. We never considered operators that are of such big size, right? So we have to think a little bit, what would happen if L is of order n? Now, if L is of order n, you have an operator whose size is of order n. Let's see, so here, any diagram that would be non-planar was suppressed. So if I have this diagram here, let me draw it in green, this propagator that would pass on top of these ones and connect like this, that would be non-planar, right? This stuff here, where I connect like this, this is suppressed. Now, why is this suppressed, this diagram? It's suppressed because we lose loops. We lose powers of n. You agree? On the other hand, note that when you decide where is this propagator going, there are like order L options, right? So if L is 10, there are more or less 10 bad diagrams that you don't consider. Okay, so even if you sum all of them, 10 over n goes to 0. But now that we say the size is equal to n, there is a competition. On the one hand, the diagram is suppressed. On the other hand, this diagram, there are L options where to connect to. Whereas neighboring graphs, you only have one option. You go to the left or you go to the right. So all planar graphs have this locality built in. That when you are drawing the graph, everything is local because you are drawing it on the plane. When you go non-planar, you get non-local. So you get extra factors of volume. So if your graph is very big, even though the diagrams are suppressed, because the entropy is so big, there are so many options to connect, they are also important. So when we conclude that when L is of order n, now higher genus matter as well. And in particular, when you have a string, it means that this correlation function of a string to a string is much bigger to a correlation function where a string breaks into two. But now, when L starts to be of order n, if you consider this very big, here L is of order n, and you consider this big 2-point function, you can convince yourself that this is of the same order as a 2-point function where you would actually emit a small closed string. Whereas these guys are big, and this is big. And this would be of the same order as the diagram where you emit two small closed strings. Right? Again, I'm saying that I have m to the capital L that scales like n, m to some L prime that also scales like n, could be L. And then these guys are of order 1, and all these graphs are of the same order now. Whereas here, no, this was much bigger than this, that was much bigger than this. And so what happens is that when L is of order n, this object now is a good object that sources closed strings. It becomes an object that has no problem producing closed strings. And what object in string theory is the source of closed strings? Yeah, D brains. And so the idea is that as n becomes large, this type of objects, the proposal, the guess, again, this is just a tentative dictionary, is that these guys will now correspond to brains. Brains are objects that like emitting strings, that are the sources of strings. Like charge point particles are sources of electric field. And what if L is of order n squared? Well, now the higher genus dominates. You want to produce strings. It's the few strings that are suppressed. Now, this diagram is much smaller than the diagram where you emit stuff. Because there are so many options to choosing emitting stuff, and higher genus are enhanced. So now you have an operator that you put, and it wants to create infinitely many closed strings. Right? So what object in nature you put that wants to produce infinitely many closed strings that include infinitely many gravitons? It can be anything that is big enough to deform a geometry. Right? If it's an object that is so big that you should describe it as a coherent state of infinitely many particles, like a geometry. A geometry is what? Is a coherent state of many gravitons. It can be a gravity wave, it can be a black hole, it can be anything. But it's an operator that is so heavy that is deforming the geometry. And so this operator would be a geometry. These operators would be geometry deforming objects. Like black holes, like gravity waves, like any object that is so heavy that it back reacts on the geometry. And that's indeed the kind of object that we have in string theory. In string theory, we have strings that are just probes, light objects that move. D-branes that are heavier. They are still probes. They still barely deform the geometry, but they are heavier. They are now planes that can source closed strings. And if you put many D-branes, like stacks of D-branes or other objects that are even heavier, now they become very heavy and they can deform the geometry, and they would be things like this. And all this, just this large n counting, gives us some intuition that this object should exist and so on. Okay. So this would be a good point to stop. And next week, we try to put all these things together, AdS, large n, and so on. And we will get finally to AdS CFT.